Can you see?
Okay, welcome. Yeah, thank you. Welcome everyone. Hello everyone, and welcome to the Center of Econometrics and Business Analytics in our series. Today we are having Alessandro Casini from Room Tour Vergata University, and we will talk about heteroskedasticity and autocorrelation robust inference. So may we interrupt you during the talk?
Yeah, sure. Feel free.
Okay, thank you. You can start.
Okay, so thank you for organizing this virtual seminar series. There are several seminar series around online nowadays, but I think they are mostly US based. I think this one is more, from the list of speakers I've seen, is most Europe based. So I think it's very good that you organize it, and thank you for inviting me. So my plan for today is to full screen. My plan for today is to give an overview of some work I've done on our inference in the last 3-4 years, rather than just present a single paper, which I think it will become too much technical and also will be only results from a single paper. So I'm going to give an overview of some work I've done on this topic. So our inference is just, as I said, heteroskedasticity, autocorrelation, robust inference, and basically involves computing the statistics and confidence interval in the context of potentially serially correlated data. The most popular approach in economics is to use so-called standard error estimator, which stands for heteroskedasticity autocorrelation consistent estimator, going back to the work of Newey, West, and Andrews. For example, you take a linear regression model. You know that if you have a set of correlation to errors, then the asymptotic variant of the square estimator is not the usual one. And the key idea of Newey, West, and is just to say, you can still use OLS, plus you correct the standard error for serial correlation, and then you can just use the same critical value you will use with the ID data. Everything will converge to a standard normal for a t-test, and so on. However, this approach, OLS plus HAC, has been criticized since the mid-90s, because it was noted that if you have strong dependence in the errors, then test statistics normalized by Newey, West, or Andrews lead to tests which can be oversized a little bit. So you over-reject. And some alternative been proposed in the last 20 years. The one which has received most attention is so-called fixed B, our inference, which was introduced in a series paper by Kiefer and Vogelsang. And fixed B stands for the bandwidth. They keep the same estimator, the same Newey estimator, but the bandwidth is kept at a fixed fraction of the sample size. This means that when you use the Newey West estimator, you include all lags, not just a few lags like as recommended by Andrews, but you use all lag autocovariances. And they show actually this fixed B can achieve better size control. However, all this work, especially the fixed B, most of this work, and especially the fixed B, relies on stationarity, covariance stationarity. So you need to have a stationarity error and regressor for the linear model. And which again, stationarity means time invariant moments. So the moments are constant over time. And also, as I will show later, if in the context of the linear model, if you assume the error regressor stationary, implicitly also requiring that the model is correctly specified. I'm going to give some example where misspecification can violate the stationarity assumption. Okay, some form of misspecification. And however, we all know, as we also have worked on some of these topics in time series econometrics, that economic time series are highly non-stationary. The moments of the time series can change over time. There is evidence of time-varying parameters, time-varying volatilities, breaks, structural change, regime switching. These are all features that make economic time series non-stationary, highly non-stationary. For example, sometimes some of this structural change may be related to changing preferences, to changing technology. And other times they are just associated to major events such as the COVID pandemic or the financial crisis. This can induce changing the moments of the main macroeconomic time series. And in the case of stationarity, I will show that the existing approaches suffer from can suffer from size distortion and power losses. So in particular, you have probably now the opposite problem here. You have under rejection under the null hypothesis and lower power under the alternative. And the intuition for this is that the traditional long-run bar estimator or estimator are contaminated by non-stationarity. What happens is that the non-stationarity makes the series appear more persistent. Because the series appear more persistent, traditional estimators are like inflated. They become very large. And when you normalize for a test statistic by a standard an estimator which is inflated, the test loses power under the alternative, and the null just under it has rejection rate below the nominal level. So for example, here, if you get a long run bar estimator which is inflated by non-stationarity, when you normalize, for example, the test, the statistic becomes smaller in absolute value, so you end up with low power. And this is I'm going to provide some theoretical results, more intuition for this, for why non-stationary generates this problem. And so what we do is, so in this project, what I've done is to relax the assumption of covariant stationarity, allow for some form of misspecification, and I propose a statistical framework for non-stationarity. In particular, we introduce a class of processes that have a time-varying spectrum, and meaning time-varying second-order properties. And in this context, I propose a new estimator, which is a modification in Western Andrews. And the key feature that it allows for, it applies smoothing, parametric smoothing also over time. And all the theory developed in this paper concerning the estimators developed under non-stationarity, including optimality and the mean-square error criterion and data-dependent method for the selection of the bandwidths. So the new estimator, which is named DK-HAC, double kernel estimator, applying the smoothing of autocovariance lags like the usual UV West, and in addition applies smoothing over time to account for non-stationarity. So we have two bandwidths here. And in final sample simulation show that under non-stationarity, the new estimator performs better. It doesn't suffer from this non-monotonic power or power losses. And okay, these are the paper I'm going to rely during the presentation. I think the first one is the one I rely mostly. It's the one which introduced the new estimator, the DK-HAC estimator, introduced this framework based on evolutionary spectra or spectra, time-varying spectra. And then in another paper, we propose a new pre-whitening procedure different from Andrews pre-whitening to apply to the DK-HAC estimator. Again, this pre-whitening is supposed to better account for non-stationarity. And in the presentation, there are no theoretical results, but in the simulation, I included the pre-whitening DK-HAC. And then I will also show some results on the comparison on the theoretical properties of the new method with the existing method, including the fixed B, which are from this paper here. Some theoretical results on power and the bias of the long-run bar estimator. And then there are also some new results on fixed B and the non-stationarity, where in this paper I derived the fixed B limiting distribution and the non-stationarity. Also studied the ERP, which is the error rejection probability of the test, the fixed B test. And the ERP is just a measure of how good the asymptotic distribution is, how good is the approximation provided asymptotic distribution. Okay, and these are more or less what I'm going to show. Okay, let's start with a very simple example, which is also like a leading example. So suppose we take a linear regression model, we want to make inference about beta naught, and we allow for certain correlation the error term ET. We can just use the least square estimator, and we know the asymptotic variance of the least square estimator is given by this expression here. The two matrices on the sides are easy to obtain since xt is observed. So anything we have to do is to estimate this matrix here in the middle. In the presentation, I'm going to refer to this matrix here as JT matrix, and in econometric jargon, an estimate of this matrix is usually called, or at least at the beginning of the literature, it was called as HAC estimate, so heteroskedasticity and autocorrelation consistent estimate. And notice that we've changed the notation. We call VT equal xt time ET. But if you take a test outside the linear regression model, you will still need an estimate of this JT The only difference is that the VT will be some other process, still satisfying the same assumption, still zero mean, finite moments, and so on. And okay, once you have an estimate of this JT, that's important because if you want to conduct inference, for example, you want to do a t-test and f-test, and you absolutely need such estimate. For example, take a t-test and the R element of beta, you need the R diagonal element of H, which uses the JT estimate, okay? And we know result from statistics so that under stationarity, the limit of JT, which is this longer run variance, is equal to 2 pi times the spectral density of frequency 0 of VT, okay? And this is the usual setting. So the problem is to estimate this JT matrix or the limit of JT, okay? And the seminal works here in econometrics are Andrews and West. And the key approach of Andrews and West is that the estimator they propose is consistent for the limit of JT. So you have a consistent estimate. This means that when you normalize a test by this consistent estimator, in the limit, the denominator will converge to a constant. The randomness only comes from the numerator. And so you will have the usual asymptotics, the conventional asymptotic, and for example, the test will convert to a standard normal. This means, if you have correlation errors, once you correct for the asymptotic variance of the statistics, then you can still use the same critical value you will use for, in the case of IID data. So it's like, for example, two-sided t-test at a 5% significant level, you can just use 1.96, okay? That's the key intuition behind U-West, consistent longer run variance estimator, which leads to conventional asymptotic distribution for the test statistic. And again, this was criticized because if there is substantial dependency in the error, then this t-test can be oversized. You reject too much. And this led to the second part of the literature, post Andrews and West. Here there has been lots of work, many alternatives being proposed. And for example, the t-statistic approach of Abraham and Mueller, and then the fixed B, which is the one I'm going to mostly focus on, and the one which is received most attention. There are several papers in Econometrics on fixed B. And again, it was proposed by Kiefer and Vogelsang. And the key difference from the New West approach is that the fixed B estimator is inconsistent for JT, unlike Andrews and New West. This means that when you normalize a test statistic by this inconsistent estimator, in the limit, the denominator does not converge to a constant anymore, but it remains random. So you have randomness in the numerator and randomness in the denominator. This will change the asymptotic distribution of the test statistics. So a t-test will not follow a standard normal anymore, but will follow some non-standard fixed B distribution. Then in the case of stationarity is pivotal, so the critical value can be obtained by simulation. And there has been many refinements of this method. Also recently, there are some papers in Econometrics by Stock, still based on fixed B. And this leads to mostly for concise distortions and the stationarity when there is strong dependence in VT. And they show that the fixed B is able to reduce these
May I ask a question? You mean non-stationarity, not unit root non-stationarity, but something like conditional heteroskedasticity, right?
Like Brecht's regime switching. So as you said, excluding the unit root, so excluding the infinite second moments. So finite second moments, but the moments can change. You have a structural change, regime switching, time variable parameters.
So-called non-stationary volatility, right?
Non-stationary volatility, yeah. But not unit root, so the point is that in this problem, we need this matrix to be bounded, right? In the unit root, this will not be the case. So for this problem to be well-defined, infinite second moments cannot be allowed. So unit root is excluded. And they are inference.
This is like non-stationary volatility as in Cavalieri and Taylor papers, right?
It's one, not only that, it's more than
not only. Okay.
You can have like regime switch structural change, then also in the regressor you can have change in the mean.
Okay.
Like general stationarity of an otherwise covariant stationary time series in the case, just time varying moments.
Okay. Thank you.
Thank you for asking this question. I think.
And one comment about Ibragimov and Miller paper, as I understand, they allow time-varying moments, and their test is robust to time-varying moments because we need only asymptotic normality for their estimator.
Yeah, I will have one slide later on the t-statistic approach, the connection between what I'm doing and the t-statistic approach. But you are right, the t-statistic approach is like the fixed B, it is valid under non-stationarity, this kind of non-stationarity. And I will have one slide later in the presentation and, on the average null t-statistic approach. And because there is some connection between what I'm doing and this approach.
Okay,
it's not straightforward, but I think we share something. But later I will have one slide dedicated to this. So here it's most about fixed B. This slide, this at the beginning at least. So yeah, fixed B. So and the most focus on stationarity with strong dependent, they show that using these fixed B asymptotics with long bandwidths actually reduce the oversized problem. So they perform better than Numi West than just using HAC. And however, on the non-stationarity is completely different picture. And the method that does worst on the non-stationarity, that suffer most for this non-stationarity is indeed fixed B. And then we show later the reason is that it uses too many lags. And when we have this stationarity using too many lags, it generates too much bias in the estimator. But I will give more detail later in the presentation. And okay, let's review how this HAC and fixed B work. So remember, we need to estimate JT matrix, and by using changing variable, the JT matrix can be written as the sum of all autocovariances of the whole gamma k, where gamma k is just an average of the autocovariances at the lag k. And yeah, and the classical estimator Newman West and Andrews are defined here. They apply a kernel K1, which assign different weight to different gamma at K. And the gamma at K is just a simple analog of the true gamma K. Just take the average of the simple autocovariance of the two pair BT at and BT minus K at, where we replace the unknown error term by the square residuals. Okay. And B1 is the bandwidth, which is satisfying some condition here. And for Newman West, K1 is the Bartlett kernel, which assign triangular weights, while for Andrews is the quadratic spectral kernel, which is optimal and the mean-square error kernel. And this is the Newman West estimator. As you can see, it uses the first ST autocovariances, and it has these triangular weights. The fixed B is the same as Newman West estimator, but it uses all autocovariances. You can see ST is a truncation lag, while the fixed B estimator uses all simple autocovariances. Also, the bandwidth is this form here, so it's giving more weight to simple autocovariances. And again, this is under the asymptotic where B1 go to 0. This is consistent for JT, while this one is not. That's the key difference between these two approaches. And the fixed B, the new result about the fixed B is in this slide. So originally it was shown that under stationarity, for example, you take a t-test based on fixed B, the numerator will converge to the standard deviation, the longer run variance time a normal, and the denominator, the fixed B estimator, converges to this element here. And you can see that the nice feature that under stationarity, the square root of the longer run variance is proportional. So it appears in numerator and denominator just cancel. So at the distribution become pivotal. This is a Bryan bridge. B1 is a Bryan bridge, and B1 is a W1 is a linear process. So everything is pivotal. You can simulate the distribution to obtain a critical value. However, showing one of the paper I have that under non-stationarity this is not the case. The fixed B distribution is not pivotal. And the reason is that the longer run variance is time varying. So you don't get this, it doesn't cancel, it stays inside the integral. And also the denominator becomes much more complex. So the denominator depends on the longer run variance in a very complicated way. The longer run variance in this case is just a nuisance parameter. And this sigma u is just the local longer run variance, the longer run variance time u. Since we have time varying moments, the long-run bar is changing over time. And again, the fixed B distribution under non-stationarity depends on the second moments of error regressors. And the non-stationarity therefore also affects this error rejection probability. So it turns out that under stationarity, the ERP of the t-test based on fixed B is smaller than the ERP of t-test based on new surrenders, but this does not hold anymore under no stationarity, just because you pay the price that the distribution is non-pivotal. But I will give more detail later. Okay, so you have a big difference from the stationary case. The critical value that you have been used so far under stationarity for fixed B are not valid under no stationarity. Okay, so the distribution is different. Okay, let me give some example why it's interesting to consider no stationarity or time varying moments. So I will have 5 points. I'm only going to discuss 3, 4, and 5. Point 1, it just says, if you have margin changes the marginal distribution of the regressor, for example, some breaks in the regressor, time varying volatility, or regime switch is something, then this generates no stationarity in BT. Similarly, if you have a stationary regressor, but you have no stationarity in the error, like time varying volatility in the error, then again make BT no stationary. Then another example that I think it is of interest. So if you have familiar with structural change model, think about your linear models, like there is a break in the parameter of interest beta naught. You know that if you don't account for the break, then everything is inconsistent, or your estimate of beta naught will be inconsistent. And however, if you use some models such as structural change model, regime switching model, which would be the appropriate thing to do here, then you know that you are going to get an estimate of this break date T naught. It's like the way it works that you split the sample in 2 parts. You estimate beta naught in the first part. In the second part, you estimate beta naught plus delta naught. And this is consistent. I mean, the estimate of beta naught and delta naught are consistent. And however, with no result is that you only have consistency for the fractional break date, but not for the break date itself. Thus, the break date itself will be Go1. So the estimate.
Alessandro, I'm sorry. What is T0? What is T0?
The break date. This
is break date.
If you look in the title of the slide, there is T naught is like there's a change in beta naught at date T naught.
But why it's not consistent? We can estimate this, for example, by minimizing of sum of squared residuals, for example.
You can estimate consistency beta naught and delta naught, but not T naught. What you can estimate consistency.
Is
fractional break date. Yeah. So here, what you get the consistency for the fractional break date, which is between 0 and 1, what the break is, but the break date itself is not. This means that when you use, anytime you use this method, or anytime you have some breaks around, you have a precise estimate for the fraction, but the exact point, the break date, you cannot consistently estimate. So you are imprecise. You are around the break date, but you never claim that your estimate of T0 is the good estimate, because you are not. It's not consistent. So you are going to be close to it, but you never split the sample at the right point. Well, of course, unless the break is very large, just because you have this big O result. This means that even if this is sufficient to give consistent estimate for beta naught and delta naught, since the fractional is consistent, the fact that you have this inconsistency for T0, it generates some local misspecification. Since you never split the point and the sample at the right point, locally the residual will be contaminated. And so it's like you are inducing no stationarity in the residual. You have bias in the residual locally, just because of this feature that you cannot get a consistent estimate of T0. And so this generates a local misspecification. And again, no stationarity again. And in this kind of models, it is well known that like even the New West and Andrews can give problem for like rejecting hypotheses about the parameter, like tests for structural change have problems under the alternative when you have breaks.
I'm sorry, why can we not get the T0 exactly that? Again,
T0 is it's like you only have consistency for the fractional break date, which is between 0 and 1. So this is the fractional break date is defined as T0 divided by T, this one here. That you can get a consistent estimate of this number between 0 and 1, tells you where the break is in the unit interval. it is consistent at rate t, so fast rate of convergence, but by definition, you don't have consistency for the actual break date. It's like you only have a tick point. There is no way to get information about this. Only for the you have sufficient information for the fraction, but not for the break date itself.
Well, if we search for a break date,
yeah,
just like as Anton said, just like what was this paper for this? Mohammed Chan's paper on looking for the break date by literally minimizing MSF over T.
Yeah.
Why is it not consistent for T?
For T is not, it cannot, it will not result in structural change. Even like Bain Perron, this is a result in Bain Perron. You only get consistent for the fractional. Of course, you have an estimate for T naught at, you have an estimate, but that estimate is not consistent. It's only consistent the fraction.
And the reason is,
think about what you really need is to estimate beta naught and delta naught. It's where you are using suppose you have only one break. You are using the first part of the sample to estimate beta naught. Even if T naught is not consistent, the fraction is. So this is sufficient to get beta naught estimate consistent. So it's like the T naught is like a tick point. You cannot get a consistent estimate for T naught. Only the fraction you can get it. And this is sufficient for the model to work. Beta naught and delta naught are consistent just because of the fractional. That's what you need.
Okay, yes, I see. Okay, that's fine. Yeah, thanks.
If you think that T naught is not consistent estimable, this means that you are going to get an estimate of T naught. And because only the fraction is consistent, your estimate T naught is close to the true T naught, but you can never say is exactly T naught because you have inconsistency. So you are around the true point, but you can never say is the right point.
Mm-hmm. Yeah, okay, thanks.
Can generate some local misspecification. In particular, if you look at the residual when you estimate this model, you look at the residual around the change point, you will see some kind of non-stationarity because it's not exactly that point where you split it. So you have kind of shift in the mean of the residual around the change point. And this can affect the standard error. Okay. Then another example about misspecification. So suppose you have a linear model, you just run regression YT on XT, and later in the sample, there is a new regressor WT, which is independent from XT, that becomes relevant, but you don't include in the regression. In this case, the true error term will be ET star, but even if ET and XT are stationary, your true error term ET star will be non-stationary, just because you have misspecified the model. So this is saying, if you require covariance stationarity in XT and ET, this kind of situation where WT is not including the regression, and this does not affect the consistent estimation beta naught because WT is independent of XT, then the covariance stationarity in the error and the regressor requires that the model to be correctly specified. It does not allow for this situation because the true error will be non stationary. So covariance stationarity also rules out some mild form of misspecification, which can be relevant in practice. Sometimes a new regressor becomes relevant in some part of the sample. You don't have information for this. You just run a standard regression with the full sample, and this introduces some misspecification. Then another relevant point is that there are many tests in econometrics, really many, where they have the characterizing feature where under the null hypothesis, everything is stationary, but under the alternative, you have no stationarity. Think about tests for structural change, where you have no structural change under the null, but structural changes under the alternative. Tests for regime switches, same story. Then there are tests for forecast evaluation, like a double Mariano test, where you have equal predictability under the null and unequal predictability under the alternative. So under the alternative, you have time variation forecasting performance. So this you are dealing with no stationarity under the alternative hypothesis. Then tests for time varying parameters and so on. So these tests, the features were stationary null, no stationary alternative. And in this context, there's been documented that the power under the alternative can be influenced by this non-stationarity, and when you use the long-run bar estimator, the Econometrics West renders, you can have problem with power just because induced by the non-stationarity and the alternative. So again, these are some examples, and it seems to be relevant even in, back to 1995. Stocker-Watson mentioned that 70–80% of the main macroeconomic time series were non-stationary. So it's like there is strong evidence of non-stationarity, and we want to understand what are the properties of this DK-HAC estimator and the non-stationarity. And okay, I have some simulation just to give some and sort of anticipate some of the problems. So the red are the classical Econometrics West renders with pre-whitening and different method to compute the bandwidths. The black is the fixed B, and the EWP, which is the equally weighted periodogram, is a method proposed by Stock in Econometrics and 2021, I guess. And it's an orthogonal series estimator based on frequency domain, essentially. And the blue is the DK-HAC, the one I'm going to propose in this presentation, and I'm going to give more detail later and just reporting it for completeness. Okay, so in model M1 we have I do a t-test on the coefficient of the stochastic regressor, and we have no stationarity in the errors. Particularly, it's an R1 the error, but the coefficient R1 is changing over time between 0 and 0.8. Then in the last part of the sample, ET is just a stationary R1 with strong dependence. And XT is an R1 with a medium dependence, 0.4 the regressive coefficient. This is model M1. Model M2 is a misspecified model where we have this similar to the example discussed above. We have WT, which is independent of XT, and but this is not included in the regression. Okay, and you can see that the size for a 5% nominal level, KBB, fixed B, and the EWP, and they reject systematically. So the rejection rate are very low. Also, New West with pre-whitening is under rejecting. New West without pre-whitening is here's a little bit oversized, but then there is evidence of under rejection also here. The DK-HAC are doing reasonably well, but there is also here some evidence that they are also fighting with this under rejection. But again, here the point is that if you have no stationarity, either the errors or regressor, or you have some form of specification under the null, you may have under rejection. And under rejection under the null may have consequences for power. The power of KVB, as you can see, is much lower than the power of the other test. Also, pre-whitening is lower than the other test. And there's also for model M2, sometimes the rejection rate at KVB are very, very low. And they go, the power of all tests is monotonic, is going to 1, but the KVB and pre-whitening in West they have lower power. Okay. And this is for the case of the linear regression model. If you go to t-test outside the linear regression model, like the double Mariano test, a test for forecast evaluation, now here, under the alternative hypothesis, the size of the report was fine for all tests, more or less. But the power, under the alternative hypothesis, you can see that there are instances of non-monotonic power for the KVB and the EWP. The power converges to 0, actually, so it's like non-monotonic. And same is true for pre-whitening, and with pre-whitening, also New West and with pre-whitening. The only one who's doing well is New West, but it's not really doing well. It also has no monotonic power because it goes from 0.81 to 78, while the DK-HAC have good monotonic power. So here, again, in this test where you have stationarity under the null and stationarity under the alternative, there are serious problems with the existing methods for power, instances of non-monotonic power. And so why there are these problems? So some of these issues already been discussed via simulation that, it is well known that you're testing for breaks under the alternative hypothesis. Sometimes the test is not able to have power, and this is problematic, and is often attributed to the long-run bar estimator, biased the long-run bar estimator. Mostly these are results of simulation. Also in statistics, custom type tests have this kind of problem. This is mentioned in JASA. And the point is that, as I said at the beginning, this kind of stationarity makes the series appear more persistent. Traditional long-run bar estimators are inflated. Normalizing a test with an inflating long-run variance leads to power losses. So why there is overestimation? This we can connect to well-known results in time series. if you think the uniroot problem, when people are testing for uniroot, sometimes if the true process was stationary, but it had some structural change, then tests for uniroot tend to give uniroot. Again, this kind of stationarity plus breaks, so no stationarity, make test for uniroot, make the seed appear as if it has a uniroot, even if there is no uniroot. So make the seed appear more persistent. And similarly, in the long memory literature, it is well-known result that you can generate long memory if you take a short memory process and you add breaks. So if you take an ARMA process, you add some breaks in the parameter, the autocorrelation function of this contaminated short memory process may look like the autocorrelation function of a long memory process. So where you have a stronger dependence. And this is what the kind of some result that relate to the intuition for this problem with DK estimator. Let me give an example. So suppose you have a non-stationary VT, which is VT is equal to V1T for the first 10% of the sample, and then is equal to V2T for the second part, for the remaining 90% of the sample. V1 is a stationary one with strong dependence. V2 is a stationary one with small dependence. So VT overall is not stationary. A plot of VT is here, one row. So you can see that even if V1 and V2 are both zero mean processes, the sample average of in the first part for V1, the first part of the sample shift away from zero. This is just to reflect the fact that you have a short sample with strong dependence, and it's like the shifting. It's like similar to say that there is a shift in the mean, but there is no shift in the mean. The mean is zero. This V1. It just happens because you have a small regime combined with strong dependence, while V2 bar is close to zero, and you can show for this process, in general, sorry, that if you take gamma at k, remember new West and fixed B are based on simple autocovariances, so this gamma at k, you can expand it in this way. You can show that in the limit this is equal to the weighted average of the true autocovariances at the lag k for in the first regime and in the second regime. So gamma 1 is the autocovariance of V1, and gamma 2 is the autocovariance of V2. So you have a weighted average of these two regimes, plus you have this bias term, which we call it low frequency contamination bias. And this bias term just account for the difference in the mean of these two processes. And notice that you have a difference in the mean square, so it is going to be positive. Then PI and PJ are just the length of the regimes 1 and 2. So you have everything positive here, but then there is a plus in front. So this bias term is always positive. So this means that if this kind of stationarity can generate upward bias for any simple autocovariance. Since the new West and fixed B are weighted sum of simple autocovariances, you may get inflated standard error just because of this low frequency contamination bias. In the linear model we have seen in the simulation, and also here, the mean of V1 and V2 are zero, so asymptotic this term should not be there, and this just results as a final sample bias. For example, here, if you replace the mean by the sample average, you will get a number greater than 1 here, this is something close to 0. So when you replace this by averages, you get something greater than 1 squared positive, then you have these two numbers positive, so you get some bias in final sample here, in this example, for example. And this is a final sample bias. In contrast, for the case of double Mariano test, you have no stationarity under the alternative. So in that case, this term here is not asymptotically zero. This is non-zero also asymptotically. So you have bias also asymptotically. That's why we had much more distortion for power for the double Mariano test. Just because the feature of this test, when we have no stationarity under the alternative, it leads to this non-zero bias asymptotic. And remember, under the alternative double Mariano test, you're trying to forecast something, you have two models, you are comparing two models. Under the alternative, you have either one model doing better or the other. So you have this time variation forecasting performance and the forecast losses between the two models. This is what generates this non-zero bias here. Okay. Under the null, you have equal predictability, so you have zero mean under the null. And one property is that, of this result is that this contamination term does not depend on K. So for each k, it is the same. This also means that, for example, if you take k large, we know by mixing properties that the first part here should converge to 0, because for k large, the dependence of like k should go to 0 between bt minus k, but the second term does not depend on k. So the more lags you use, the more bias you get, upward bias you get. And for fixed b, it's even worse, because fixed b uses all lags, even very large lags. In the limit, even if the true dependence should be 0, they will still get this positive bias. So there will be more bias for fixed b than for new West renders. And this is what we've seen in the simulation. The fixed b had much more problems in terms of under rejection, lower power than other methods. And okay, now let's introduce the new estimator. I need to go faster. So the new estimator, the DK-HAC estimator is again, we want to allow for non-stationarity, so we want this expectation to depend on t, not just k. So we apply a second smoothing over time. So the first part of the estimator is the same as New West. There is a kernel k1 that give different weight to different gamma at k. But now our estimate gamma at k is different. It's different because now what we are doing, think about splitting the sample in blocks. And for each block, we estimate this CT hat. And CT hat, think about CT hat being an estimate of this expectation for T in the R block. So for each block, you get this C hat, and C hat is like an estimate of this where T is in the R block. The way it works is that we apply a new kernel, non-parametric smoothing over time. This kernel K2 gives different weight to different pair of observation. More weight is given to pair of observation that are in the R block. And then you take an average over the blocks. This is so the difference in the new DK estimator that it applies smoothing over time, not just use the simple autocovariances like for New West. It's not taking an average of all pairs, but we applying the smoothing over time just to account for non-stationarity. And this kernel K2, you can plot it here. So different bell, the action of the kernel K2 for different blocks as R as the index of the blocks. So as R move from the beginning of the sample to later in the sample, the bell moves from left to right. The first bell has a different shape because it accounts for boundary effect. And if you think about New West, which is not applying any smoothing, then you can think as giving unit weight to all pair of observation, which is the red broken line. Okay. And again, this is how, just to give an idea how this non-parametric smoothing works. What we do, so we propose first a framework for BT and non-stationarity. So we consider data generating processes where the parameter can change continuously and discontinuously. We allow for smooth changes in the parameter and also breaks. We name this class segmented locally stationary. Then these segmented locally stationary processes have time-varying spectrum, where the spectral density depends on the frequency, but also on time. And you can show that the autocovariances for segmented locally stationary processes actually depends on the spectral density at time t. So the autocovariance inherits property of the spectral density, the smoothness of spectral density. In the segmented locally stationary processes extend the locally stationary introduced by Dallows in statistics. And one property is that, unlike the stationary case where we have this nice result where the limit of JT is equal to pi times the spectral density frequency 0, under non-stationarity or under segmented locally stationary, the limit of GT is given by this expression, is like the integrated local spectral density over time. Under stationarity, this f will not depend on u, so we come out the integral will reduce to this result here. All the results in my project are derived under this framework, so we develop results for JT hat, assuming BT is segmented locally stationary. Okay, asymptotic result, I'm just going to give an overview. There are results on consistency, rate of convergence of JT hat. We derive the mean-square error of the estimator. We determine the optimal bandwidth. So now we have two smoothing, so two bandwidths over lags like B1, and also the additional bandwidth for smoothing over time. And we use the plugin approach to determine data-dependent bandwidths, where we replace unknown quantities in the optimal formula by consistent estimates, similar to what Andrews did. Then we develop minimax MSE bounds, which are sharper than Andrews bounds that are based on stationarity. So one feature of this segmented localization that if you impose a restriction on stationarity, like segmented localization, you can update sharper bounds. You can get to obtain more precise mean-square error bounds. And this is why we can get some, we can improve some result in Andrews. And also, using this framework, can develop asymptotic expansion to show what is the ERP of this new test relative to existing test. And data dependent bandwidth. So I think I need to speed up a little bit here. I'm going very fast. So we derived the mean-square error of the estimator. It depends on these two bandwidths and the kernel. We minimize the mean-square error relative to the with respect to the bandwidth. So we found the bandwidth that minimize the mean-square error of the estimator. This gives us formula, closed form formula for the optimal bandwidth. There are some unknown quantities. It depends on the property of the data. We replace them by consistent estimates. I'm just going to discuss how to obtain this. One quantity is this one, which is the most tricky one, is phi2, which depends on the spectral density of VT and the second derivative of the spectral density. The spectral density is the second derivative. So here we follow what Andrews did. Since VT is unknown and also the spectral density is unknown, one way to obtain this estimate for phi2 is to make a guess about VT. And Andrews, the guess of Andrews was that VT was following R1. Here they are in a stationary context, so we assume that we guess that VT follow local stationary R1, where the parameter change over time. Given this guess, you can obtain closed form expression for f and the second derivative of f. But you can see that they only depend on the parameters of this model. So you can just replace this quantity by consistent estimate. You can just use, for example, LS over only windows, or just use non-parametric kernel methods to obtain an estimate of alpha and estimate of sigma. Then you plug them here and you have your estimate of phi2. What happens if the guess is not correct, which usually is the case in practice? It happens that the estimate of phi2 is still consistent. It will not be the optimal one. But you know, this still gives you a feasible method to obtain data-dependent bandwidths. And again, the difference that we assume local stationarity, since you are in a stationary environment, rather than just stationarity as assumed by Andrews. And the ERP, so the error rejection probability. There's been lots of attention on this ERP on Econometrics, result in Econometrics by Jensen and Sun, Phillips, and Jean show that the ERP of fixed B is better than the ERP of HAC and the t-test based on estimator. So consider the following t-test. You have a t-test based on estimator like Andrews New West. DK-HAC is the t-test based on the proposed DK-HAC estimator, and then you have the usual fixed B. The asymptotic expansion Velasco and Robinson show that under stationarity, the ERP, which is given by the leading term in this expansion, the ERP, think about the ERP as being the rate of convergence of the test statistic to its asymptotic distribution, okay? So the faster the rate of convergence, the smaller is going to be the error. And Velasco and Robinson show that for HAC estimator, the ERP is this TB1T to the power of minus one half. So, and then later result by Jensen, Econometric, and Sun, Phillips, Jean, Econometric under stationarity show that for fixed B, the ERP is much smaller. So you can see that why fixed B provide high order refinements under stationarity, because the ERP it's smaller than this ERP here. This holds under stationarity. And this has been justified with no result, justified the use of fixed Bs in the last 20 years, just because of this better approximation it provides. The picture is very different than stationarity. We develop asymptotic expansion and stationarity. We show for HAC estimator, the ERP remain the same under stationarity. And for the DK-HAC estimator, the ERP is similar, somewhat similar, a little bit larger than for the HAC estimator. And then we compare it with the ERP of fixed B under stationarity. Recall that the fixed B distribution was non-pivotal. And this non-pivotality is a big price because the ERP of fixed B actually increases substantially from the stationary case. From this rate, it goes to this rate and become larger than the ERP of HAC estimator. So while under stationarity, fixed B was clearly better because it's a smaller ERP. Under non-stationarity, the opposite happens. Fixed B is the method that has a larger ERP relative to HAC and DK-HAC. So it's like it is not optimal under non-stationarity, unlike the stationary case. And again, this is what is written here. Jensen and Phillips show under stationarity RP of fixed B is more than RP of HAC, but under non-stationarity the opposite occurs. So the indeed is similar, or it can also be large. So fixed B doesn't seem to be optimal under stationarity and no stationarity, sorry. And small sample analysis, again, you have some simulation, again, t-test in the linear model, t-test outside the linear model, like double Mariano test, Giacomini Rossi test is our test for forecast valuation. We compare the same estimator. This is a stationary case with strong dependence and 0.4 the dependence in the first panel, the second panel 0.9. So you can see that with strong dependence, fixed B is the one and the stationarity is doing better. And also EWC a little bit oversized, but the fixed B is the one which is the best size. The pre-whitening, the Andrews and pre-whitening, the Andrews and New West are oversized, as we will know, result in the literature. So you can see the oversize can be substantial. When you use the pre-whitening, which was proposed by Andrews, the oversize reduced substantially, but still not is not as good as fixed B. The DK-HAC without pre-whitening can also be a little bit oversized, and the pre-whitening with the one we propose in the other paper actually is the one we recommend because it achieves better size control. So we hope this is somehow competitive to fixed B, even if fixed B and the stationarity is like the first best for size control. The power, of course, is fixed B is the best, but also has a lower power. So but this is somehow can be attributed to the usual size power trade-off. Is the most accurate size, but you also have some lower power. And DK-HAC has higher power, and also, of course, Andrews West has very high power, but they were highly oversized, so they are not really competitive here. Here we can compare DK-HAC with pre-whitening and fixed B, and you can see there is some gain in power using DK-HAC and pre-whitening. This is the model we have seen at the beginning, the simulation seen at the beginning of stationarity in the error generate under rejection fixed B and classical HAC with pre-whitening. And the rejections consequences for power, again, fixed B lower power than the other methods, also pre-whitening in New West with some lower power. Again, stationarity generates is somehow consistent with the theoretical result I showed you before. And this is a test for forecast evaluation, similar to the double Mariano test. Also, this test has a stationary null, no stationary alternative, again, no monotonic power for existing methods, severe problems, also for New West and Andrews here. Andrews with pre-whitening somehow is doing a little bit better, but it's still very far from the DK-HAC. And again, this is double Mariano test, what we have shown before. Again, no monotonic power just because of this alternative where you have no stationarity. And yeah, we also have theoretical result on power confirming the simulation. We show that for the double Mariano test case, the t-test is actually converging to 0, which explains the non-monotonic power. Same is true for fixed B, and we also show that the fixed B, the t-statistic fixed B is smaller than the t-test of based on HAC. So which again say that you are going to have more problem with fixed B than with the HAC. DK-HAC have monotonic power, so the statistic value, the statistics increase, and then alternative hypothesis leads to monotonic power. Again, it is remarkable that HAC and DK-HAC lead to tests which do not increase with delta, which is the value of the alternative hypothesis. So again, saying that you are going to have a problem with power, and DK-HAC leads to consistent tests. It's the only test that guarantees monotonic power for all kind of non-stationarity. This is the slide I promised at the beginning, the relationship between what I've done the statistical approach of Rajiv and Mueller. Also, some of you I've seen online, you have papers on the statistical approach. So the statistical approach, just as a quick review, is saying, you have a full sample, I can split in Q blocks, Q groups, and I can estimate each beta in each, I can estimate beta in each group. And so then I get an average of the beta across groups. There are Q groups here, and then you normalize by the variance of the beta J across groups. And this test, t-test, will follow asymptotically a t-distribution with Q minus 1 degrees of freedom. It is valid under non-stationarity, as you mentioned at the beginning. And the relation, what I see here, that there is a relation with what I'm doing, and I think it's a different way to account for non-stationarity. Here, now remember, in my case, we have this, the longer unbound estimator is applying smoothing over time over blocks. Here you are doing something also with blocks, but it's a different way. The difference is that in the numerator, in my case, is still beta eta, don't change in the numerator, while here you're also changing the numerator of the t-test, and you are doing estimation in blocks, and also change the variance estimator. You are not using a consistent longer unbound estimator, but they are using this asymptotic variance for beta j et. So it's I'm sympathetic to this. It's like it shares something with my approach, and presumably this blocks accounting for non-stationarity in this way. And one difference that the DK-HAC can be applied also outside the t-test. You can also apply another test outside the linear regression model, while this one, just by look at his name, it just, at least so far, it is only applied to t-test, so t-statistic. So, but you know, it is, as you said at the beginning, it is valid under non-stationary, also this one, unlike fixed B. So I'm expecting this to have less problem than fixed B. And okay, the conclusion. So economic time series are non-stationary. We develop a theory for evolution expected for our inference. We propose this new estimator which applies smoothing over time. We show it flexible account for non-stationarity. Existing method, both the classical ACT and fixed B, may have problem with this low frequency contamination bias. And we show that the newer inference test based on pre-whiting DK-HAC can achieve reasonable size and monotonic power for non-stationary and stationary cases.
Thank you, Alessandro. Very interesting talk. Any questions?
Yeah, it's interesting. So there's double smoothing.
Yes.
But I wonder, so there's the smoothing over the legs.
Yes.
That gets you different weights on all cross products of the residuals. Then there's the smoothing over time, which also gets you different weights over for each cross products. And so in a sense, this is doing the same thing twice.
Let's go to the estimator.
Yeah, let's go to the estimator.
This is the first part is the smoothing over lags, which is the same as Newey West, K1.
All right.
There is inside this gamma at K, this is okay, Newey West is this one. Inside gamma at K, we apply the smoothing for the same autocovariance.
Yeah, so VV prime has the cross products of the residuals that are weighted with K.
Yeah, so yeah,
summed over time, right? And then you have the legs K1, which is applied to the sum. So what it gets you is really the same sum of the cross products of residuals with just different weights.
Different
so
way. Yeah, you can
in a way, I guess if you write it out, it would be a bunch of cross products of kernels and the residuals.
Yeah, you can.
So I guess ultimately there will be some, you could in principle replace it with a one weight, which will just be dependent on lag and time, right?
Yeah, you can also rewrite this as a single kernel giving weight as a function of time, a single kernel as a function of time and K. And yeah, you can rewrite it maybe in this, you can see it in this way. But essentially you are smoothing over 2 dimensions.
Yeah. So basically the reason you want to have explicitly the 2 kernels is, I'm guessing, because it's simpler to look at the asymptotics of that. Yeah,
but you're right, there is double smoothing. So you can also potentially write as a single kernel as a function of 2 variables, the T and the K, and maybe it's rewriting in a different way. Yeah. The smoothing over K is important because otherwise you don't have the consistency. Why the smoothing over time just to more flexible account for non-stationarity.
And so, and when you talk about misspecification, you talk about the misspecification of non-stationarity. Could you think about having another form of misspecification on top of non-stationarity?
So the misspecification, the example I had was this one. Okay, so you have a linear model, you want to infer about beta naught, but you forget one of the regressor. Okay, you don't include in the regression this WT, which becomes relevant later in the sample. Think about, you have a model, you start with the right model, later a new regressor become relevant, you don't include in the regression, you have a misspecified model. In this case, I call it a mild form of misspecification because WT is being uncorrelated with XT, your estimate of beta naught is still consistent, even if you don't include the WT, just because they are uncorrelated. And this is a mild form, a small.
Yes, I see that. So this is the type of that I would call misspecification through non-stationarity. But if you have misspecification, so suppose that there is a W that is missing, and you have a non-stationarity bit with the indicator function is there. What changes?
What do you mean by non-stationarity with the indicator?
So there is this specification has a non-stationarity there that's emitted. So it's a misspecification through an emitted non-stationarity.
Yeah. So
my question is, what changes if you have misspecification by an emitted variable, but not a non-stationary, but non-stationarity? See what I mean? If there's a WT, but it's not through non-stationarity, so that it doesn't change at certain t. It's just not there.
If WT is stationary, it still gets the same problem because what generates the problem is the fact that you omit it. That's generating non-stationarity, because without the omission you have the error is ET, but if you have the omission, the variance of the true error ET star will change. Because before the change you all have ET, then after you have ET and plus WT, so the variance changes no matter what is WT, even if it's stationary WT, the variance of ET star will be no stationary. So you have the same problem more or less. It doesn't matter whether WT is stationary or not. The fact that there is a change, that's enough.
No, I see that it doesn't matter if it's stationary or if WT is stationary or not. But what if there's a WT, which is the way you describe it, and there's a ZT that you emitted, so that there is an additional layer of misspecification.
Okay.
That has nothing to do with non-stationarity.
So as long as it's uncorrelated with XT, it gives the same problem. The important is that to generate this problem, you need to have to be relevant. This ZT should be relevant only in some part of the sample, not the full sample. Otherwise, it's like a new error, a different error, but it doesn't change it.
Okay, yeah. So I see. So that's just like an emitted variable bias. So you would have an issue with consistency of beta 0, but it won't translate into the consistency of the variance estimate.
Yeah, no. Everything here is under the condition that the least square is consistent. Okay, so small form of misspecification such that the least square is still consistent. Otherwise, the estimator is not valid. The standard error, we cannot even discuss them. We can make it invalid, right? So this.
And if it's conditional heteroskedasticity with a misspecified process for it.
Yeah, if we still have condition for least square consistency, then it's still within this framework.
It's still work. Okay, I see. All right, cool. Thanks. Yeah.
May I ask some general question? What do you think about such thing? Recently, I looked through the paper of Peron about comparison between GLS and HAC inference, and he argued that HAC inference give inconsistent estimators, and it's better to use GLS, not HAC or HAC. What do you think about this?
Yeah, he has in mind the situation where you don't have zero correlation between the error and the regress. So he said there are sometimes in economics you have like forward-looking variables, so where you lose this weak exogeneity assumption, where if you have dependency in the error. And I said in that case the HAC will not be even be valid, and he proposed this GLS. But I mean, in those cases, I think those situations are quite not extreme, but economists don't think about that to be very super relevant, at least so far. Maybe it's going to change, but so far, or less plus HAC has been, people think about it as being valid. It may not work perfectly, as we show, because of the size, but at least valid, people assume it is. Meaning that you have what you need to be valid, you need to just have the consistency for the square estimator. So XT and DT being correlated. But he's thinking about a situation where this may not hold if you have these forward-looking variables and you have dependence in the error. But yeah, it's a kind of that paper you mentioned, that note. It's a kind of give a different view, it's opening questions. This is like the OS plus HAC is the one that has been used so far, has become most popular based on US essentially, and yeah, he's saying that the assumption will not be satisfied. So it's a controversial view, but I'm sympathetic to the discussion. Yeah, GLS. The problem with GLS is that if you don't make the right assumption, then you lose the consistency, right? GLS, you need to make assumption about the errors. You need to make the right assumption about the errors. While OS plus HAC is just whatever is the error, I just estimate the longer run variance consistently. GLS might misspecifying your assumption about the errors, then you lose the consistency for the GLS estimator. So it can be problematic. So this one disadvantage. That's also why I think in economics has become relevant to use OS plus HAC and not GLS, because GLS is seen to be too risky.
Yeah. Thank you.
Welcome.
Any other questions? No. Okay, thank you again for very interesting talk. Thank you for presenting your works at our seminar.
Thank you very much for inviting me, for organizing. It's very nice. Thank you. Alessandro,
Are you in the same department as Tommaso?
Yeah, Tommaso project, yeah.
Okay, well, send regards to him.
Okay, I will for sure. Thank you very much.
All right. Thank you very much.
You're welcome. You're welcome.